Hello again, Earth Science, and welcome back. This is Chapter 4. We're going to talk about Earth's formation today. Now that we've talked about mapping, and we've talked about how we can look at Earth, let's talk about how it formed. So geology, remember, was the study of the planet Earth. More importantly, we're looking at its composition, its formation, how it has changed over time, and how it continues to change. So in this graphic here, I've got the breaking apart of Pangea. Earth looks drastically different than it used to, and it continues to change. We have fault lines that are moving, and we have plates that are moving every single day. So first, we need to talk about how did our Earth actually come to be in the solar system, and how did this solar system originate? Well, with science, we believe in the nebular hypothesis. This is one of the hypotheses for the solar system formation, where 4.5 billion years ago, a large cloud of dust and gas existed, and it slowly rotated around in space. And over time, due to its own gravity, it shrunk down on itself. And as it got smaller, its rate of rotation increased. This is the same way as like if you've ever watched a figure skater, if they go from their arms out to their arms tucked in, they speed up. It's the same thing. As this big ball of things is getting smaller, it's starting to rotate faster. Most of this material in the cloud kind of gathered towards the center, and this made it very, very hot. And then we got hot enough that hydrogen atoms actually started to fuse together to form helium atoms, and this hydrogen fusion is what created our sun. Jupiter would do hydrogen fusion if it was a little bit bigger, but it's not quite big enough to get to that heat that it needs to start hydrogen fusion. So now that we have the sun, we have the other 10% of the material that was in that accretion disk, that disk of gas and clouds and dust. This material started to condense due to friction, started to condense due to electromagnetic, like positive and negative charges being pulled together, and gravity pulled all of this together to form solid chunks of ice and rock. Now this ice and rock continued to accumulate into bigger and bigger masses until we had planetesimals. These were like little baby planets. These structures continued to compress and they started to spin much like our sun, heating up. And eventually these condensed masses of rock and ice would become the moons and the planets that we see in our solar system today, and the asteroids and the meteors and all of that good stuff. We are the third object from the sun. And because of our spinning motion, Earth has the shape that it has today. And you might ask, what is the shape of the Earth? You might say sphere, you might say flat, just kidding. But the Earth is shaped like a sphere, but it has a bulge in the center. It kind of at the center is a little bit bigger, and we call this shape an oblate sphere. So when someone asks you what the shape of the Earth is, you say it's an oblate sphere, because you're that much smarter now. So how do we know that the Earth isn't perfectly round? Well, we can look at the photographs taken from space, but unless you've got like a really well-trained eye or you're using some kind of computer software, the Earth still looks pretty spherical from space. But we can actually measure the weight of things on Earth to figure out how close they are to the center of the Earth. So weight, remember we talked, is different than mass. Weight is the force of gravity as it pulls on an object. So the farther from the Earth's center, the heavier an object is. So since we have more Earth at the equator, an object weighing 194 newtons at the poles weighs 195 at the equator. So which object is closer to the center of the Earth? It's going to be the one at the pole. It's going to be closer. It has less Earth in between it and the center. So the Earth's interior, the original surface of the Earth, looked very much like the surface of our moon today. At this point in time, Earth was probably the same type of material all the way through. But Earth frequently collided with other elements left over from the creation of the sun in the form of asteroids and meteors, and possibly like a whole another moon-sized object hit the Earth in its early formation. And this kind of helped to differentiate and create the planet that we have today. One of the most important driving forces on the Earth's early formation was friction. As these objects were colliding, they were producing heat. Earth collided with a lot of nickel and iron, and the heat from these collisions caused these metals to melt. When we talk about density in science, we're talking about the amount of mass that occupies a certain volume. So this is why wood floats and iron sinks. It takes a lot more wood to be the same weight as an equal mass of iron. This is because iron is much more dense than wood. There's more mass per volume than a chunk of wood would have. So because of this, objects that are denser than other objects will sink below lighter substances. And this happened with these metals. And in the same way that oil and water won't mix and oil will float on top of water, these melted metals separated out by their density inside of the Earth. So what this means is our inner core at the very center is composed of very solid and very dense iron and nickel. Around the inner core, we have an outer core, which is melted iron and nickel. The inner core is solid as the pressure is pushing everything together so tightly. And then the mantle is our thickest layer. And it has high levels of iron, silicon, and magnesium. It's a solid, but the high temperature and pressure cause it to act like a liquid, which is why the crust, what we're on, kind of floats above it. The crust is a thin, rigid layer of lighter rocks that includes all of Earth's surface. And there's two layers. One of them is the lithosphere, what we walk on. It's the uppermost part of the mantle. And then it floats on a kind of slush of the mantle called the asthenosphere. And these parts are kind of a little gray area on where they actually one starts and the other stops. But we kind of just float on the mantle, living our best life up here. So the heat inside of the Earth was generated from three things: the meteorites impacting, the weight of all this material causing compression, and decay of radioactive isotopes, things like uranium and carbon and iodine. All of these have radioactive isotopes that as they decay, they produce heat. This is what keeps a lot of heat in the crust going. But on the flip side, since the beginning of the Earth, we've been losing heat as well. Some rocks heat faster than others. The thickness of the crust varies from place to place. We're letting more heat out of the mantle through the crust. And the percentage of radioactive material varies. So some areas have a lot of uranium, a lot of radioactiveness, and others have very light or very little radioactiveness. So they have less heat there. So they're losing more than they're gaining. Earth has a magnetic field. This is why your compass always points north. This field is tilted about 11% away from the poles. So when you're looking at your compass, it's pointing towards magnetic north, not true north. And this is caused by the movements of liquids in the Earth's core. And just how they move, the north and south magnetic pole are different than the north and south pole of the planet. So how long does it take Earth to rotate around its axis? Well, if you're used to looking out the window, you know that we have 24 hours. There's one rotation is equal to 1 day. Each time you're going back around, when you get to noon and that sun is high in the sky, you're going to go around a whole circle before that sun goes back up high in the sky again. That's 1 day, around 24 hours. There is some evidence for rotation other than the day cycle. Jean Foucault, he attached an iron sphere to a long wire, like a really long wire, like 20 stories high. And then this pendulum went, and each hour it would switch 11 degrees clockwise. So if it started out here, going back and forth, 11 hours later, it might have been something like this. And then another 11 hours. Another 1 hour, excuse me. It would have been, oh, that's too light of a color. There we go. Then something like this. And eventually, after 8 hours had gone by, this was now a right angle to its original path. It was now swinging left to right versus back and forth. And why is this? Did this pendulum change its direction? No. In fact, the pendulum was going the same direction the whole time. The Earth was just turning underneath of it. And we could see this because we had a really long pendulum that was swinging above the Earth. If you've ever been to like a Discovery Center or a Science Center, they'll usually have a pendulum like this. It's got a little electric motor in it, and it will knock over these little pegs each hour. It's very cool. They have one down at the Boise Discovery Center. It's, I think, the closest one to us, but pretty cool little gadget. So another way that we know that the Earth is spinning is we have the Coriolis Effect. And this is the effect that winds don't blow in a straight line. Instead, they are deflected or turned. If you're in the northern hemisphere, they get deflected to the right. And if you're in the southern hemisphere, the winds get deflected to the left. And this deflection of both winds and ocean currents is called the Coriolis Effect. And we have the Coriolis Effect on other planets. We have it very, very noticeable on Venus, very noticeable on Jupiter. Jupiter has that giant red spot that's caused by its Coriolis Effect. They have much bigger storms. They have more atmosphere, much more dense atmosphere. So Earth does not only rotate around its pole. We're also orbiting around the sun. And this is the orbital plane, or this straight line here. It is not perpendicular to our axis. It is at a 23.4 degree tilt. This is very, very important because this tilt is important for a lot of things on Earth. If we had a perpendicular kind of axis, Earth would look a lot different, and it would not be as nice a place to live. So Earth makes one complete turn, 360 degrees, every 24 hours. So what we can also say is Earth rotates at 15 degrees per hour. Because Earth is shaped different, it rotates at different speeds. Near the equator, it spins faster, around 1690 kilometers per second, which is 1,050 miles per hour. And at the poles, it spins about 0 miles per hour. And this is because it's spinning around those poles. Those poles don't have to go anywhere. They're not moving any distance. So the effects we have of rotation are we get the daily change of night and day, we get the Coriolis effect, and without this spin, Earth would have one super hot side and one side that was completely frozen, just like our moon, which is trapped around us. It's what we call tidally locked. So one side of the moon is always facing Earth and the other side is always facing away. So early man measured time based on the sun's location. The sun will rise in the east, have noon at its highest point, and then set in the west. But solar noon does not occur at the same time everywhere. It moves westward about 15 degrees an hour, or 1 degree every 4 minutes. So we had to figure out some way to measure time that made sense once we decided to travel faster than horse and carriage. And even horse and carriage was starting to push it. Once we got trains, planes, and automobiles, we had to figure out how to measure time in a way that everybody was having noon at the same time, and everybody was experiencing, what we call time zones now. So our standard time zones were created to accurately tell time and help people, mail things and get them on the right day to help set appointments and dates in different time zones. There are 24 of them around the world, and each time zone is 15 degrees of longitude apart. We call these time meridians. And these are the areas between the meridians that keep the same clock. So we're on the Pacific Standard Time. If you go one time meridian over towards the east, you're on Mountain, and then Central, and then Eastern Time. So you keep going time meridians. The prime meridian is our starting spot. That's where we start worrying about this. Moving west, so if you move over towards this way, your clock goes back earlier, and moving east, your clock goes forward to later times. On the other side of the Earth, at the 180 degree longitude line, there's the international date line. This one you either gain or lose a day instead of an hour. So instead of changing your clock, you change your calendar for the international date line. If you move west, you're moving 1 day later. If you move east, you're moving 1 day earlier. So here's our, our timeline here. This is our original time meridian where the prime meridian runs. And then all the way across on the other side of the planet here, you have this one running kind of funky here, the international date line. And the reason that this is a little funky is we wanted to include Hawaii and Alaska with Pacific Standard Time and Hawaii and Alaska time, so we were closer to the same time as them versus what they should be, because Alaska has 1, 2, and almost 3 time zones inside of it. So we wanted to make sure that they were all on the same time. Now, Earth's revolution around the sun is a little bit different, and we have evidence for this. Our constellations change seasonally. We see, Orion up here in the North Hemisphere during the winter, and we don't see him during the summer. This is caused by parallax, as our nearby stars seem to shift position in relation to our distant stars. This is hard for us to look at with the naked eye. Instead, we use instruments to kind of deal with parallax. But you can see this effect sitting in front of your screen here. So this image here is used to help you understand parallax. Pick something in the distance on this one. Pick a spire, pick that little tuft of smoke out in the background, and then you just put your thumb up in front of your face and close one eye. Now don't move your thumb, but close the eye that's open and open the eye that's closed. And now all of a sudden you can see that smoke. Oh, you can't see my thumb here, but I have my thumb up. But now you can see that smoke. That's parallax. As your point of view is changing, you're able to see things from a different angle. So Earth, we revolve the same as we rotate. We go counterclockwise as viewed from the North Pole. And our orbit is an ellipse, this kind of like oval shape. The sun is located at one of these focuses, and we don't have anything at the other focus. In other galaxies, there are suns at both focuses. On average, we are 92,960,000 miles from the sun. We have a close point when we're closest to the sun. It's our perihelion. It's the point we're nearest the sun, about January 2nd, right in the middle of winter here in the northern hemisphere. And the aphelion, which is the point farthest from the sun, which is July 4th for us here in the northern hemisphere. It's kind of weird that the point we're closest to and farthest from the sun are the opposite of what we'd expect them to be seasonally. We orbit the sun every 365.24 days. This is why every 4 years we celebrate a leap year. This is the time on our calendar when we're accounting for that extra quarter of a year each time we rotate around the sun. So here's a picture here of the Earth. And here it is when we're farther away. This is the aphelion, much farther away from the sun. This is the perihelion, much closer. Our moon has the same kind of orbit around us where it has a perigee and apogee. I'm not going to require you to know that, but it's just a nice little interesting factoid there. So what is the effects of this revolution and tilt? Since the Earth is tilted, the side closest to the sun receives more sun. It gets warmer and has longer days. So this side that's tipped towards the sun has more days. This side tipped away has shorter and cooler days. So it's the Earth's tilt that determines the seasons, not how close we are to the sun. So when we said aphelion and perihelion are opposite for us, that's because even though we're furthest away, when we're furthest away, we're tilted towards the sun. So we're getting the most sunlight, getting heated up, and this is when we have summer. If Earth was straight up and down, perpendicular, we would have no seasons. We would have 12 hours of darkness, 12 hours of daylight. If we had more tilt, if we were pointed more towards the sun or more away, we would have hotter summers and colder winters. Now we have solstices. We have a summer solstice and a winter solstice. In the summer solstice for the northern hemisphere, this is when we're tilted towards the sun to our max. This is when we have the longest day of the year, or the most sunlight, and it is June 21st. The sun is directly over the 23.5 degrees north latitude, and we call this line the Tropic of Cancer. Also on the first day of summer, every line to the north of the 23.5 degree of latitude has 24 hours of sunlight. So 66.5 degrees north, we also call the Arctic Circle, and they have 24 hours of sunlight during this time. On the other end, we have the winter solstice, which begins on December 21st, coming up, only a couple months right now. It is the shortest day of the year, and the northern hemisphere is tilted away from the sun to the max. The 23.5 degree south latitude has the sun directly above it, and this is the Tropic of Capricorn. And during this time, the Arctic Circle gets 24 hours of darkness. And then in between the solstices, we have equinoxes, and equinoxes means equal night. And this is exactly what happens on these days. The daytime and nighttime are equal. So we have 12 hours of daytime and 12 hours of nighttime. The vernal equinox, or the spring equinox, happens on March 21st, and the autumnal equinox, or the fall equinox, happens on September 22nd. And on these days, the sun is directly overhead the equator, instead of that 23.5 degree line on either side. So I hope that you've learned a lot about Earth, about our rotation, about kind of our formation, about why we have seasons. This is going to be really important when we talk about winds and waves and frost wedging and all of these very important processes for Earth. And the more we know about how we formed and how the Earth actually works, the bigger picture we get to paint. So I hope you enjoyed this video, and have a wonderful rest of your day.